In this video, we are going to go over graph theory for weighted graphs, specifically the Chinese Postman problem. So first we're going to talk about a trail. That is a walk that repeats no edges, and then a circuit is a trail that starts and ends at the same vertex. So a Eulerian trail is a trail that traverses all the edges of the graph, and then a Eulerian circuit is a circuit that traverses all the edges in the graph. So what we are going to do in order to traverse all of those, we call it the Chinese Postman problem. So the first thing is this finds the root of least weight around a weighted graph and returning it to the starting vertex. So one thing we do need to know is it is not possible to have an odd number of odd vertices. So there is a way to break that down so we are able to find that root of least weight. So the first thing is we need to identify all vertices with odd degree. We then need to list all possible pairings of the odd vertices. And then next, for each pairing, identify the shortest root between the paired vertices and find the sum of weights of the edges involved. Now here's the thing. The shortest root might not mean the least amount of vertices used. So you do need to look at those weights. And then fourthly, choose that pairing with the smallest combined sum. What's going to happen is we're going to add those extra vertices in to connect them so we don't have those odd vertices. And then you literally make a big loop around the graph where you hit every single edge and connect back to your starting point. So here is our first example. We want to solve our Chinese Postman problem. The first thing we need to do is find our odd vertices. So if we look at A goes to B and A goes to F. That is two edges, that is even. So we're looking at ones that have odd edges, and that would be B and E. So what is the least weight path from B to E? That is going from B to C to E. So we need to connect in an extra edge from B to C. And again, since B to C is weight 4, that new edge is going to be weight 4 as well. And then from C to E, we connect another edge in with weight 7. So we are beginning and ending at A. So we need to start at A. We need to make sure we go through every single edge, including the two we added in, and where we end back at A. So sometimes it's kind of a little bit of a puzzle. We need to make sure we hit everything. We can't re-go through an edge or a path. So we kind of need to maneuver, and sometimes it takes just a little bit. Nope, that didn't work. Let's try again. So on this one, we're starting at A. In A, we can go to B, B down to C, C to D, D to E, E to F. I like to kind of mark them and number them so I know what's been used where. So from F, if we go up to A, you can see that we don't have everything highlighted, so that would not mean we've hit every single edge. So from F, we cannot go up to A. Instead, that means we need to go to B or C. In this case, we're going to go to B. Then we can loop on our added edge down to C. And then from C, we can go down to E, loop back up to C, go to F, and then up to A. So then we can talk about our path. And again, that's why I like to color and label it. So then I can easily write it out. We go A to B, B to C, C to D, D to E, E to F, F to B, B to C, C to E, E back to C, C to F, and then ending back at A. And then we add those weights and we get a total weight of 59. So on this one is a larger graph. We have a lot more to kind of analyze. We have 4 vertices with odd edges. So we have A, B, D, and H. So we need to pair them. And we have A and B and D and H. So what are the pairings of least weight? Well, from A to B, that least weight is going to be just A to B, 38. But then D to H, if we notice, there's no direct connection. So we need to look what is the connection of least weight, and that is through G. So D to H is going to be it's going to be 23 plus 26. Add that to AB, which is 38. So that whole path or grouping is going to be 87. So that is one pairing of our four vertices. We need to list all and determine which one has the least weight. So we could have AD and BH, and then those pairings would give us a total weight of 116. We could pair AH and BD together, and those groupings would give us a total of 120. So since AB and DH is the fastest, that is the least weight, those are the extra edges we're going to add in. And again, you add in those weights as well. So we need to find the possible route he could take in order to minimize the distance he walks. And so for that one, we start at A. We need to go all the way around, hit every single edge, and end back at A. So again, highlighting it, you can walk around. This picture is really small. On my personal notes, I did walk through everything and highlight those edges, but our path would be A to B to C to D to E to F to D to B to A to H to F to G to H to G to D to G, and then end back at A. So if you notice, we did have A in there more than twice. It was in the middle as well as the start and the end, and that's because A was one of our odd vertices, and so we did have a link back in, and that's why it appears more than twice. So adding that together, we have a total weight of 613. So a friend offers to pick him up from vertex H and take him back to A. Would this decrease his length? And the answer is no. And let's think about why. That weight from H to A is 35. And so H wouldn't be an odd vertex anymore. So then our new added path to make sure we didn't have those odd vertices would be ABD, which is a weight of 126. So with having H as an odd vertice, we added in paths that was a total of 87. So 126 minus 87 is a weight of 36. If he was to pick up the friend at H and take him back to A, that would be losing out on a weight of 35. 38 is larger than 35, so there is a larger weight with taking out H. And then for C, state where you would advise the postman to collect. So this is us thinking about what odd vertex should we take out to maximize, and that would be at B. B would maximize, or taking B out would maximize because you take that odd vertice out. So then our repeat would be D to H, which is a weight of 49.